Okay, let's start. We talked about functions, for instance, f from set A to set B. And remember, a function for each element little a of the set A gives a unique element little b of the set B. And what is the range of that function? The definition of the range is all values fa of the function. Okay, so fa is the value of the function.
Excuse me, sir.
Yes, thank you.
The screen share.
We can see your share screen.
Thank you. So, one moment. Okay, I hope you can see now. Now, for some of you, this picture may be helpful. Think of the set A as this blob, and think of the set B here the element A in this set, the element B in this set. And then we can think of the range like this. Imagine for each element we have an arrow. Then the range, I'll do that again. The range is the subset of B where all the arrows point to. But B we call the codomain, and A we call the domain. So, example, for f from R to R, given by the formula x squared, A is the real line. Let's put 0 here. And B is also the real line. But I'm going to write it as vertical real line because I'm thinking of the graph. Now, what is the range? Well, we know that if I take 2 points x and minus x, then these both go to the same point x squared. So in this case, what is the range? It's the subset of the real line given by positive numbers and 0. Okay. So any more questions about that, let me know. Ways to measure temperature. The Fahrenheit scale and the Celsius scale. So if I know the temperature in Celsius, this is the formula to work out the temperature in Fahrenheit. And we could write this as a function. Let's call it little t for temperature. We could write this as a function r to r. So as input, this function takes a temperature in Celsius, and as output, gives a temperature in Fahrenheit. So for example, 0 Celsius, freezing, goes to 32. 100 Celsius, boiling, goes to 212. But we have a choice about what codomain to take. So remark, if we take account of absolute 0, so that's approximately minus 273 Celsius. Then instead, we can take a function t, which has domain minus 273 to infinity, and codomain r. Then, what is the range It's the value of the function at minus 273 up to infinity. Okay, so I'm just going to put in brackets the range of this function is also R. Okay, so another function example. This one is from the textbook. Yeah. Yeah. Just trying to copy picture from textbook. I should do this. Yes. Okay. Yeah, so now it works better. Okay, example. Some box is made by cutting and folding like this. Write volume V of X. So solution the box is a cuboid so if we know the lengths of the sides, say A, B, and C, then we can multiply them together to get V equals ABC. So what are the lengths of the sides? Well, we cut out 4 squares from the corners, and then we fold. And after the fold, this length is A. This length is B. And C equals X. So we can see A is 22 minus 2 corners of length x. B is 14 minus 2 corners of length x. And C is just x. So V is this product. And I can rearrange this a little to get this. Okay. So now what is domain of function? Well, I think if I'm going to make a box, its volume should be more than 0. So to make a box with volume more than 0, I need this inequality to hold. Okay, do you see why? Because if 2x is larger than 14 up here, then, well, the cutting doesn't make sense. So my function f should be from the domain 0 to 7, open interval, to r plus, and this function takes x as input and gives this as output. So question you might ask, what is range? Of f? Seems like there is a maximum possible volume. But what is it? So answer, the range is some open interval 0 to b, and we can find this later. And that kind of calculation is obviously very useful. So some notes. in this case, the range is not equal to the domain. Oh. Range is not equal to codomain. And another note, so we could allow box B equals 0 also. If we explain what we're doing, so then f is a function from 0 to 7 closed interval to r plus. So like last time, we have a choice of how we define the function. Okay, so here's another example. Say a cone is made by cutting and gluing like this. And then the question is, write the height h as a function of x. So solution, the circumference of the circle in A is 2 pi times the radius, which is 4. But the circumference of the circle in B, now let's see. So this, this is the circle in B. And if we see how it is made of a part of the circle in A. So the length of the part of the circle in A is 2 pi times 4 minus x. So let's write this as C. Now we also know that C is 2 pi r, because the circle in B has radius r. And rearranging this, we see that r is 4 minus x over 2 pi. Now, we wanted to calculate the height h. So we can do that now with Pythagoras' theorem. Two of the sides. Four and r. So the other side h is related like this. So let's simplify this a bit. So this 4 squared cancels with the 4 squared from this 4 when I expand this square. And what I get, please tell me if I'm wrong, is 2 times these two terms yes, minus x over 2 pi all squared. And I'm going to take out 1 over 2 pi from this and get 8x minus 1 over 2 pi x squared. So again, let's write that as star. Now this implies that h is equal to that formula for x star. But now what should the domain be? Let's look at the picture again. It's like this, maybe. So for the cutting picture to make sense, we need the circumference of B to be positive. So we need 2 pi 4 minus x to be positive. So let's take domain (0 to 8 pi. So this means that x is positive and the circumference of b is also positive. So the picture makes sense. So let me just write down what our function is. So the function now is f from this open interval to r plus. Input is x, output is h, and I'll just again write it's this square root. And because it's a square root, I write r plus. But it would also be okay to write r. Now, so sketch the function f. So let's do that at the beginning of next period. Thank you. Oh, sorry. I just realized we have 10 more minutes. So after that 1 minute break, let's continue. Okay, so we sketch the function. Let's consider star, which was giving h squared as this function of x. So this is quadratic, so can draw a parabola. So like we did before, let's first calculate the axis, x. So that was minus b over 2a. And minus b is the coefficient of x, which is minus 8 times 1 over 2 pi, but that will cancel. And 2a is minus 2, 1 over 2 pi, times 1 over 2 pi, but that will cancel. So the result is eight pi. So RHS, right-hand side, factors into 1 over 2 pi times 8x, and this. So we can calculate the value on axis by putting x into this formula. And we can also see that the roots are 0 and 8 times 2 pi. And as we saw before, these are the x-intercepts of our graph. So now we can sketch x and h squared So the x-intercepts are 0 and 16 pi, and the axis is at 8 pi. The value on the axis is four, and we have a minus here, so the parabola opens down. Okay, so not the best sketch, but it's good enough. So this graph shows how h squared depends on x. So in particular, we can see maximum h happens here. And then we can look back. Okay, I'm going to bring the picture down here. Yeah, so if you think about this picture, if you imagine the cone, you can see that if we only cut a very small x here, then the cone is very low. But as we cut larger x, the cone gets higher, and then yeah, so this 0 to 8 pi this here is the domain of our function. Okay. So I'll just start another topic, curves. Maybe described by multiple functions together. So what do I mean by that? So for example, x squared plus y squared equals 1 makes a curve in the xy plane. Just makes a circle like this. So how can we describe that with functions? I'll start with that in 5 minutes. Okay. Okay, so I tried to explain a bit more what was happening in the example. So maybe some confusion was caused because there are two different circumferences. So on the page now, you can see circumference of A, that's blue, and circumference of B, that's red. So if you're still confused, please look over the details again, and if there's still a problem, then let's discuss later. Okay. So some practical things. I'll make a new page. Okay, first thing, so I do not have access to WeChat now. Temporarily. If you need to contact, please contact me by email. Some students now do this. So special reason course enrollment. So I contacted some students and we'll add them a few days. Please message or email. Again, if you still have difficulties. So thanks for your patience. There were some delays in arranging this. Okay, so about homework. So question. So please answer on Jumo. Does everyone know what to do with homework? So hand in before this Thursday. That's of course China time. And so I know many people did, but please read homework FAQ. So that's available here on Learn. Okay, so I'm coming back to Jumo to see if there are any questions. Okay. So I see some questions, but I think the answers to those questions are on Learn. So homework was set last Thursday and is due this Thursday. That's it. Okay. Any more questions? Okay, thank you. Then I'll continue. Okay, so this curve can be described by two functions. I'm going to call them f and g. So f has domain 0 to 1. And its value is the square root of 1 minus x squared. Oh, mistake. Minus 1 to 1. So this function f makes the top half of a circle like this. And then we can write a function g to make the bottom half of our circle. like this. So why is that? Well, let's sketch F. So that is a graph y equals square root of 1 minus x squared. So the x-intercepts are given by setting y equals 0. And y equals 0 if and only if this is 0, if and only if x is minus 1 or plus 1. Okay, so someone asked, do we always have to use arrows? So we could also use if and only if here. Okay. And the y-intercepts are given by putting x equals 0, square root of 1 minus 0 squared, so y equals 1. So we see that the graph of x must go through these points. And in the same way, we see that the graph of g must go through these points. So what's the range of the function now? So range of g here, we can see from our sketch, is minus 1 to 0. So a question from earlier, what's the point of codomain? Why not just make codomain smaller so that the range equals codomain? So answer, it can be hard to calculate range. For example, box example above. Okay, next point. Piecewise definition of functions. So functions can be defined differently So for instance, using a different formula in different of the domain. So we write it like this, example, a function f takes x as input and gives back one if x is 0 or less, and 1 minus x squared if x is 0 or greater. So graph what does it look like? Well, for x 0 or negative, the value is 1. And then when x is greater than 0, the value starts to go down. So for instance, we can see from the formula when x is 1, then the value is 0. So could describe the height of a ball dropped at time x equals 0. So I'm holding the ball at height 1, holding it, and then at time x equals 0, I drop it, and the height goes down like this. So another example, x goes to floor x, so that's the largest integer such that that integer z is less than or equal to x. So that's pronounced a floor. Okay, so let's draw the graph. Well, if x is zero, then the largest integer with that property is 0. And that's still true all the way to 1. But when x is 1, the largest integer with that property is 1. And that's still true all the way up to 2, and so on. So we get a graph like this. Okay, and of course it carries on in both directions. Okay, next. I want to talk about increasing and decreasing functions. So this is a property of a function on an interval. If I take function y equals x squared, draw a graph, graph is this. Then here, the function is decreasing. And here, the function is increasing. So here's another example, y equals x cubed. So how to sketch? Well, first thing, for x positive, we know that x cubed increases faster than x squared. And also, if I know x cubed, I can calculate the cube of minus x. That's because the cube of minus x is just minus x cubed. So if I can sketch the positive half of the function, if I can sketch the part where x is positive, so saying that goes up faster than x squared, so I'm drawing like that. If I can sketch that, I can sketch the part where x is negative, because the value at minus x is the value at x, but negative. Yes. Okay. Oui. So that's the graph. And looking at this graph, we can see as x increases, y is always increasing. Okay, let's do one more example. Example y 1 over x squared. So to sketch, use that if I want to calculate 1 over x squared, this is the same as calculating one over x squared. So we can use the sketch from above. So here, x is big, small. Whereas here, x is small. So 1 over x is big. So if x is big and then 1 over x is small, then 1 over x squared is also small. But as x gets smaller, 1 over x gets bigger. So its square also gets bigger. Okay. And we can see that when x is 1, then y is also 1. So we have this point. And also note that if I know the value of y for x, then I also know the value of y for minus x, because one over minus x squared equals just 1 over x squared. So the other half of the graph I can see from the first half that I drew. Okay, and now where is this increasing and decreasing? So for negative real numbers, it's increasing. And for positive real numbers, it's decreasing. Oh, so I should be careful the way I've drawn it here. So I'm going to write open circles here. So note because function not defined at 0, I draw like this. Okay. So we've seen how to do some graphs. So now let's see how we can use the graphs we know to make more complicated ones. So first, vertical shift. So if I have a function f, the graph of function fx plus k is given by shifting up k if k is positive, and down minus k if k is negative. And of course, if k is 0, it does nothing. So let's do an example. If fx equals x cubed. So first, let's take x cubed plus 1. So we're taking this same graph and we're shifting up 1. So previously, the graph met the x-axis and the y-axis at 0. But now, because we shifted up by 1, the graph meets the y-axis at 1. Okay, so what are x-intercepts? Well, we set y equals 0. So we get this equation, 0 equals x cubed plus 1. And we can factor this. And we can see that x equals minus 1 is a solution. So minus 1 is an x-intercept. Okay. And another example, if fx is x plus 1 cubed. So what have we done here? Instead of adding 1 after we do the function, we've added 1 before the function. Let me explain what I mean. So so this will give a horizontal shift. So if h is positive, I'll shift left by h. And if h is negative, I'll shift right by minus h. Okay, back to this example. So in this case, h equals 1. So we shift left by 1. So in our graph from before, the graph went through 0, 0, but now I'm going to shift that to the left by 1. Look at this. So what are the x-intercepts now? Y equals x plus 1 cubed. We let y equals 0 and then solve. But this is easy. For the right-hand side to be 0, x plus 1 must be 0. So x has to be minus 1. And but what about the y-intercepts? We set x equals 0. So y is 0 plus 1 cubed, which is 1. Okay. So another way that graphs are related is by scaling. So for c greater than 1, I have c times fx is vertical stretch by c by factor c, and 1 over c fx is vertical compress by c. Okay, so just continue, and fcx is horizontal compress by c, and fx over c is horizontal stretch by C. So we'll do an example after the break. Hi, so thanks for your questions. About the cone example, so there are a few questions saying maybe there's a mistake in the in the example. I'll go back and check after class. So if there is a mistake, I will let you know. So question. So should we always use if and only if? Well, answer, it depends. So for example, a very simple question. So y equals x squared. If x is 2, what is y? Well, solution. So if x equals 2, then that implies that y equals 2 squared is equal to 4. So note, if and only if would not be correct here. Because if y equals 4, then can have x equals minus 2 also. Okay, so this means implies, or just then, and this means if and only if. Okay, so next let's do some examples of scaling graphs. Start a new page. So for example, the graph of let me write this in functional notation first. So if f of x is square root of 1 minus x squared. So remember from before, the graph is a semicircle. So if I want to graph y equals 2 times square root of 1 minus x, what do I get? Well, I stretch upwards by 2. And now the intercept is 2. And let's do one more example. If I graph y equals 1 minus 2x squared, this is this case when I have a function and before I do the function I multiply by 2. So that's saying we do horizontal compress. So that's right. So the x-intercept is still 1. Sorry, the y-intercept is still 1. But the x-intercepts used to be minus 1 and plus 1. And now they're minus half and plus half. So now, ways to combine functions. So some notation. Dom f is the domain of the function f. So definition, given functions f and g have function f plus g and its domain is the intersection of the domains of f and g. So how do I define that function? F plus g. And it goes from the intersection of these domains to R. And it takes as input x and gives us output. So be careful, this plus sign is addition of functions, not numbers. So this plus sign is addition of numbers. So in the same way, have f minus g and f times g. It's multiplication. And they're all defined on domain F intersect domain G, because if X is not in that set, this formula does not give a result. You can also define quotient of functions. So given F and G as above, have function F over G and F over G goes from a set A to R. I'm going to say what set A is in a moment. But I define the value by this formula, the value of F at X over the value of G of X. And I put A to be the set of X in the intersection of the domains. So Fx is defined and Gx is defined. But also Gx is not 0. So let's do an example of these ways to combine functions. Let's take Fx is square root of X and Gx is 1 minus square root of X. So what are natural domains for these? Well, the natural domain of Fx is positive real numbers and 0. So the square root of X exists. The natural domain of G let's see, we want 1 minus X to be greater than or equal to 0. Which is the same as X less than or equal to 1. Okay, so for example, F plus G is a function from Remember, it's from the intersection of these two domains. And that is the closed interval 0 to 1. So f plus g is a function from 0 to 1. It's real valued. Takes as input x and takes as output this. So we could also make f minus g and f times g. F times g. It's the same domain. It's the product of the square roots. So how about g over f So from the definition, the domain of g of x in the domain of f intersect the domain of g such that f of x is not 0. And f of x not 0. F of x is not 0 if and only if the square root of x is not 0. If and only if x is not 0. So this set is equal to the set where x is in this closed interval such that x is not 0. And by definition, that's the same as this half open interval. Okay, so now let's sketch these functions. Well, actually, I'll copy a sketch from the book. So we have function fx here and gx here. And to make this graph, a good way to start is calculate values at 0 and then half and then 1. But how to sketch G over F? Well, this is a bit more advanced. So G over F takes X and outputs the square root of 1 over X divided by the square root of X. So that's the square root of 1 over X minus 1. So how would we make a graph of this? Let's do it step by step. Starting from easier graphs that we can calculate. So first, the graph of 1 over X. Looks like this. And the value of X at 1 is 1. What about 1 over X minus 1? Well, we just learned that we shift down by 1 to get that graph. So this point 1, 1 goes down by 1. Point 1, 1 becomes the point 1, 0. And where the graph gets closer and closer to the x-axis, that becomes the horizontal line minus 1. So now, let's make a graph of the square root of this. We use the first one to get to the second one to the third one. So at x equals 1, we're just taking the square root of 0. And as x becomes less, the square root increases from 0 . And we can see from the second graph that it keeps on increasing up to infinity. So we can see now why the domain of G over F contains 1 that doesn't contain 0. Let me do that in red so it's easier to see. So this is domain of G over F. Okay, so note a trick to help see shape of graph. Notice that for all points in the graph star, let's call this y, y squared is 1 over x minus 1. And that implies that x is 1 over 1 plus y squared. So then it's easier to sketch the graph the other way around. So I have y on the horizontal axis and x on the vertical axis. So let me get a graph like this. So then can swap the axes. Okay. So one other way to combine functions, and then the next subject is trigonometric functions. So composing functions. So what do I mean by this? Well, if I have a function g from set A to set B, and a function f from set B to set C, we have a function A to C. So this is just a small circle. So this is the composed sign. So how to say this? I'll sometimes say G, then F. Because in a picture, if this is my set A, and this is an object A in it, can go to a set B, with an element b in it. And then my function f to a set C with an element C in it. But the function g then f goes from A to C. So let's just write down the definition. G then f goes from A to C, takes A in A to the result of doing the function g and then doing the function f. Okay, so now take as an example fx defined by square root of x and gx defined by x plus 1. So the domain of f is positive real numbers, and the domain of g is the whole of the real numbers. So what is natural domain of g then f if f and g defined by formulas as above? Well, the answer is given by the following definition. The domain is D if the input is x, then the output is the value gx, and then the function f is done to get f bracket gx. Now, what is D, the natural domain? Well, for this to be defined, then I need x in the domain of G. But I also need gx to be in the domain of f. Okay, so some examples. So f compose G if f and G are shown at the top of the page. Takes f, x as input, and gives x plus 1, that's, and take the square root, that's f. And the domain D is x's that are in the domain of D such that gx is in the domain of f. Which is 0 to infinity. So gx is in the closed interval 0 to infinity if and only if, so this is a square bracket here. And square bracket means that gx is greater than or equal to 0. And gx is x plus 1. And this is if and only if x is in the closed interval minus 1 to infinity. So D is minus 1 to infinity. Okay, now using our methods from before, we can graph this function we get this. So this is minus 1 where the domain starts. The y-intercept is 1. Okay, so another example, f then g. So this is the other way around. So we start with x, we square root it, that's f, and then we add 1, that's g. And the domain of D is x in the domain of f, which is 0 to infinity. Such that fx is in the domain of G, which is R. So this is true for any x. So this is equal to the interval to infinity. So let's do a graph. So this graph is given by taking the square root graph and shifting it up by 1. So the result is this. And we can see the two different domains. that. Okay, so I'm going to check back and see if there are any questions. Okay, so don't see any questions there. Well, actually, maybe it's a good chance to go back and check the cone example. Okay, so let's go back. So I'm going to look back at the questions about the cone example. Okay, so a question from Rochester. Why we substitute x with pi but not 8 pi? Aha. Ah, I see. So I think I see my mistake. Great. Mistake as well. It's here. I'm going to put in another step here. Okay, let's check through. So the value on the x-axis was given by substituting 8 pi. Okay, that looks like 4. Oh, okay, so I'm still okay. So I think I see the mistake now. Okay, so sorry for the delay. So we substitute in x here and x here. So x is 8 pi. So here there are 2 8s. And we get 1 over 2 pi times 8 times 8 pi. So these cancel, and we get a 4. So the result is 8 times 4 times a half, which is 4 squared. Okay, so there is correction here. I'm going to continue the correction for one moment longer, because we see down here the value on the axis is 4 squared. Yes, and that makes sense because the maximum h is 4. Okay, thank you. Let's stop there. Thank you. See you on Thursday.